All right. Can everybody hear me okay? All right, so the learning objectives for this unit are for you to match descriptions of water properties, uh, understand how to calculate the height of how far water can rise, describe how capillarity works out in soils of different texture, relate three components of soil water potential to one another, gravitational, metric, and osmotic. We're going to define saturated hydraulic conductivity and describe how the soil property is related to soil uses, compare and contrast the concepts of infiltration and percolation. We're going to talk about how surface textures influence infiltration rates over time. We're going to talk about how soil stratification affects water movement. We're going to determine the difference in soil wetness coefficients. We're going to describe how soil texture and organic matter influence available water holding capacity. We're going to explain the hydrologic cycle, and we're going to talk about watersheds, evaporation rates, transpiration, interception, infiltration, surface runoff, drainage, and soil storage, and how all of these are a part of the water cycle or the hydrologic cycle. We're going to talk about how vegetation type, stem flow, soil management, and soil porosity influence the fates of precipitation and irrigation. And really, ultimately, we're going to be studying the soil-plant atmosphere continuum. So why is knowledge of soil water important? I will, of course, post this YouTube as an embedded video in the PowerPoint page, or I'm sorry, in the module page that I create for this week. I'm having issues making them show up during class like this, so I'm just going to keep moving into lecture, but just FYI, this will be posted. Okay, so a little info on the water molecule. Ultimately, we have a polar molecule, and the polarity results in many important properties with water. First and foremost, one of the most important properties about water that ultimately influences how we manage soils and water going through them are hydrogen bonds between individual water particles. Now, these hydrogen bonds have as a result of hydrogen bonding, water has really high boiling point, high specific heat. It expands when it freezes, and it has properties called cohesion and adhesion that we're going to talk about on the next slide. And there's a significant amount of surface tension. Surface tension, you can see, is represented by the spider here, who is actually able to stand on top of the water without sinking because of surface tension. So we're going to focus on cohesion and adhesion because it plays a really big role in how water is moved through soils. Okay, so cohesion is the attraction of water for other molecules. Okay, so it's cohesion is just water being stuck to other water. Okay, so this is what we see in the actual like soil pore area is just water stuck to water moving through. Okay, but adhesion is the attraction of water for other substances and surfaces. So adhesion is where water sticks to the surface of a soil particle, or water sticks to the surface of organic matter, or water is on the surface of a table, or this also helps explain how water is able to literally crawl up the sides of soil pores, and we'll talk about that in a little while. So again, adhesion is water attached to something else like a clay mineral or organic matter, whereas cohesion is where water is attached to another water molecule. So again, here's a figure from your book showing cohesion where water is attached to water, and adhesion where water is attached to the surface of a soil particle. So in the adhesion and cohesion within the soil water continuum, we see what we call capillary water, which is water in the pores. And out here in the general area, in between the pores or in between particles where the pore is, this is cohesion. This is water attached to other water. But here at the surface of the soil particle is adhesion, where water is literally adsorbed to the surface of the soil particle. And this distinction becomes important because it's what gives rise to capillary rise. Capillary rise is the ability of water to basically crawl up the sides of soil pores but it tends to be able to crawl up farther the smaller the pore is. Okay, so I want you to imagine like a tiny red hot chocolate straw versus a big old bobo tea straw. Okay, so the tiny hot chocolate straw, water's going to be able to crawl up that a lot easier. I don't know if you've ever, like as a kid or even as an adult, tried to like crawl up a door jamb by pressing your feet against one side and your back against the other and like trying to walk yourself up. But it's a lot easier to do the smaller the door jamb, right? So, um, that's kind of the idea here with capillary rise. So we have an actual equation for capillary rise to help us calculate how far water can move. And where this comes into handy is really understanding how groundwater moves up to the surface where plants are growing in soils. Or if we were to create really long raised beds and we were moving water alongside them, how far up the water can rise to get to the plants. Okay, so again, the smaller the pore, the higher the rise. So we have this equation where the height is calculated with a coefficient of 0.15. That's like a standard. It stays there. It's always there. It's a constant. And we divide that by the radius of the pore. Okay, so um, ultimately, what we find is that capillary rise occurs fairly quickly, but not very long in sand because it has really big pores, so water can't go very far. But in loamy sand, which is a little bit smaller of a pore than sand, it can go a decent amount. But when we get to in the really fine textures like clays and clay loams, the water is able to indefinitely rise to the surface. Capillary rise occurs over a much greater distance in tinier textures because they have smaller pores. Sucking up liquid in this upper right hand corner of this slide. And you can see the three blocks in kind of the middle right side of the PowerPoint slide. And you can see that it takes some time for smaller pores to move water. However, they can move it a lot farther just because it's easier for water to crawl up their tiny pores. You can see in this example that in half a minute it moved up a little bit, and then in 18 minutes it moved up about a third of the block, and by 64 minutes, a little over an hour, we've covered a little more than 2/3 of the block with water. I'm going to embed this video as well. It just kind of talks about some of the things that we've already discussed. So let's talk about some soil water energy concepts. Soil water potential is essentially a measure of the difference in energy levels between water in the soil column and a pure water reference at standard temperature and pressure and elevation. So water typically moves in some direction, all right? And soil water potential defines in energy terms just what direction that's going to be, okay? So what we know is that soil water always flows from high soil water potential to low soil water potential. And what we'll learn is that basically means that it flows from where it is wet to where it is dry, okay? So we basically come up with like units that we describe how dry soil is versus how saturated it is. Okay, so if a soil is saturated, it would take 0 kilopascals to move water because it's full of water, so it doesn't take any energy to get anymore. But anytime it gets drier than saturated, the values that we use to describe that energy become negative. Okay, so when we talk about moving from high soil water potential to low soil water potential, we're literally talking about moving from 0 to a negative number. Okay, so we're moving from wet to dry, from 0 to a negative number. All right, so the free pool, the saturated pool is 0 kilopascals, but all of that water, as you get drier than saturated, again, you're going to have negative numbers. So the more negative the number, the more tightly it's going to be held to the soil particle and it won't be available for plants. So there's several potentials that help move that water. Okay, so or not move it in some cases. So matrix potential which by the way, sometimes I call this matrix, just my brain. Anyways, so matrix potential is the attraction of water for solid surfaces. So this is literally just the attraction of water to the soil particle. Osmotic or solute potential is basically the movement attributed to salts in the solution. Like solutes, that kind of thing, will affect water's ability to move. It's kind of like in science where you learn about how, like, if you have a salty solution on one side and a water solution on the other, there's dynamics that change versus between water and water. Anyways, all you need to know is that osmotic is the solutes in soil solution. Gravitational potential is the movement of water due to gravity, and this occurs under saturation. That's important to know. Gravitational potential occurs when water is saturated. Okay. Hydrostatic potential is water movement in the saturated zone below the water table. So this is deep, deep in the ground and something that we don't usually study in soils. The total water potential is a sum of all of these things. So this is just a figure to kind of demonstrate what some of these things are. So I'm going to turn on my little pen so that I can attempt to write. Go to the next slide. There we go. All right, so I made a little graphic to kind of help drive this idea home. Okay, so right now we're not saturated. There's still a little bit of air. So we're actually at field capacity here. And we've got negative 33 kilopascals to move water, and the plant root's all happy because it can get water and it can still breathe, and things are going good. And then we go a little while without rain, and now we're at negative 1500 kilopascals. The plant's starting to get to its permanent wilting point. It's looking very sad. Things aren't going well. We're really hoping that there's rain, but then there isn't rain for a very, very, very long time, and there's zero water available. The plant has died, and we're at negative 800,000 kilopascals, and the whole story is just sad. All right. So now that we've kind of got some of the basic ideas of soil water properties and its movement, let's talk a little bit more about availability and management. So who doesn't want to start out Monday morning with some calculations? Yeah. Okay, so for our soil water calculations, and we're going to learn how to do this in lab, we're going to learn how to calculate mass water content, which is literally just the mass of water by itself in soil. So to get this, what we do is we would go out into wherever we want to know how much water there is, and we would take a known volume sample, and we'll show you the methods that we use to do this in lab. And we basically get this canister of soil, and what we call this is field wetness. Okay, so it has some moisture in it, but we don't know what it is yet. So we bring it into the lab and we weigh it. Okay, so the weight tells us the weight of soil and the weight of water. So now we stick it in the oven for 24 to 48 hours at 105 degrees Celsius until all of the water is gone. Okay, we're taking it all the way down to 0% water, negative 800,000 kilopascals, bone dry. And then we weigh it again. And we take that original weight and we subtract the dry weight, and that gives us the grams of water. But we want to actually express that as a percentage of the total soil that we looked at. So we divide it by the dry soil again and multiply it by 100, and that gives us the percent water in the soil. Now, to express that as a volume of water based on the volume of sample that you took, we take our bulk density and we multiply it by the actual mass of water that we just calculated. So don't worry about all this weirdness in the center. What you need to know, so in review, To get our mass of water, we take our wet soil and we subtract out the dry soil, and then we divide it by the dry soil. Then, to get the volume, we just multiply that value by bulk density. So in this example, we've taken a core, shown up here. Let me see if I can get my thing to work. So here's the core, and you're going to learn how to do that in lab this week. Now, I have some examples in the study guide of those calculations. If you run into any struggles with them, I'm happy to meet with you in my office. I have enough room in here that we can adhere to social distance guidelines, and I'm happy for us to both be in the same room wearing a mask to help you go over the calculations. I know calculations aren't super fun for some people, and so I'm happy to help in any way. All right, let's talk about water flow in soil. Let me check in and make sure nobody has. So the law that we essentially use to come up with the movement of saturated soil is called Darcy's law. And Darcy's law allows us to calculate something called hydraulic conductivity. Hydraulic conductivity is the amount of time, the length that water can move per unit time. Okay, I'm going to highlight it in here. All right, so the factors influencing saturated hydraulic conductivity are basically going to be any factor that influences how water moves through soil. Okay, so that will be the number of large versus small pores, whether or not there's preferential flow channels like a big old tree root that has rotted out and left a ginormous biopore, for example. Water is always going to go the easy route. Texture will have a huge influence on saturated hydraulic conductivity because texture influences the amount of macro versus micropores. So why do we care about understanding how fast or how far per unit time water can move through soil, aka understanding saturated hydraulic conductivity? Well, saturated hydraulic conductivity essentially determines the suitability of a soil for irrigated cropland, sanitary landfill cover material, wastewater or CAFO storage lagoon linings, septic tank drainage fields, and a variety of other management principles. It all comes down to how fast water can move through soil. So some examples, some typical saturated hydraulic conductivity values. We're going to look at the third column. If I can get my annotation tool. We're going to talk about how the influence of structure, texture, and land use on saturated hydraulic conductivity. Okay, so here we have a graph at the. I'm gonna skip this slide, but the moral of the story here is that the upper horizons of this soil horizon, the A horizon especially, has the most saturated hydraulic conductivity because that's where all the roots and microorganisms are working, and they're creating micropores and macropores to transmit water. But as you go deeper and deeper into the soil, especially into the BT horizons, it gets a bit more, there's not as much roots or organisms moving through to create areas for water to flow through, so it slows down significantly. So ultimately, the deeper you get in soil, the slower water is going to move. So let's talk about a sandy loam versus a clay loam over time. How far water actually moves over time in these two textures. So over on the left we have. All right. So in summary, saturation, when we're flowing in soils that are saturated, we describe it using Darcy's law, which tells us how fast water can move through soil over a certain amount of time, what distance it can go, saturated hydraulic conductivity. The factors that influence saturated hydraulic conductivity include any factor affecting the size and configuration of soil pores, the amount of macro versus micro versus biopores, and soil texture. We want to understand saturated hydraulic conductivity because it determines the suitability of a soil for irrigated cropland, sanitary landfill cover material, wastewater or concentrated animal feeding operations, storage lagoon linings, or septic tank drainage fields. I'm going to skip this slide. All right, let's talk about unsaturated flow. This takes place when the larger pores are empty, leaving only the smaller pores to transmit water. This is independent of gravity, it's governed by matrix potential, and it can be highly variable because of broad differences in soil textures. So if we have a relatively moist soil, but it's not saturated, we have high matrix potential. But if we have a relatively dry soil, we have a low matrix potential. So there's a lot of variation in unsaturated flow because of this. Infiltration and percolation is how water gets in and how it behaves when it does. So infiltration is the process at the surface that water enters soil pore spaces and actually becomes soil water. Percolation is the movement of water downward in the soil profile involving both saturated and unsaturated flow.